Hey, Nathan here. Welcome back to another game math video. In this video, I'm going to discuss matrix transformations and the mathematics behind manipulated matrices in order to understand what is going on behind the scenes when we do matrix.create translation, for example. So there are three main types of matrix operations that we will use in the upcoming tutorials. Translations, which is moving it to a vector position. Scaling, which is moving by adjusting it based on a single float value for a scale, how we want to scale the object. And the other one is rotation, and that will also be a float value, how we want a rotation. And we're going to use the z-axis. Even though it's a 2D game, we're using the z-axis to rotate in our game. So let me talk about translations, and that's when we translate, we are saying we want to move an object from one point to another. So we create a translation matrix, but then we can also do a vector2.transform of any vector we choose by that matrix. So if we have a matrix that's 1, 1, it's a transform matrix that would transform to position 1, 1. And then we transform another vector, 1, 1. We'll see what kind of result that will be. It's not going to be 1 by 1 because we are transforming that 1 by 1, 1, 1 to a different position. So let's go ahead and work on that example. So we're going to translate by the vector 1, 1. But then we're also going to transform a vector by that resulting matrix by 1, 1. Okay, so let's use yellow for the transform matrix, translation matrix. Okay, so t is equal to, we need to create translation of a vector. So we want to translate by, let's put this white and put that on the side. Translate to 1, 1. So we're going to translate to that point. So a transformation matrix, or matrix in general, is going to be a 4 by 4. We are going to operate in a 4 by 4 matrix environment. So a 4 by 4 matrix, that's going to be represented by M11, M12, M13, M14, and similarly for row 2, 3, and 4. So I'm going to pause this and finish that up. Okay. The reason I chose it this way to explain how to represent the vector, or how to represent the matrix, is that's the way that the monogame matrix is represented by. If you look at the matrix when you're running monogame, it'll have a list of properties and fields, M11, M12, M13, M14. So I'm doing it this way so you understand where you can assume that they will be. So if I say M43, if you're looking at your matrix in your code and you look at the matrix.M43, that is in this position here. Okay, so that is the matrix. Now we need to translate to 1, 1. So we need to create a translation. So I'm going to call this, I'm just going to put equals here. So a translation matrix only operates on the last row, the 4th row. This row here. M11 is going to be 1, M22 is going to be 1, M33 is going to be 1, M44 is going to be 1. M41 is going to be X, M42 is going to be Y, and if you're operating in 3D, M43 is going to be Z, everything else will be 0. So translate to 1, 1, that's going to be X here and Y here. So the first row is going to be 1, 0, 0, 0. Next one is 0, 1, 0, 0, 0, 0, 1, 0. And then 1, comma 1, comma 0, comma 1. That's X, Y. Alright, so T translated to 1, comma 1 is equal to 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 1, 1, 0, 1. So it's translated to that position 1, comma 1. Alright, so if you're familiar with matrix multiplication or matrix mathematics, multiplication in specific, you will know that you cannot just multiply any matrix by any matrix. Some of the properties need to match. We want to transform a 2D vector 1, comma 1. We want to transform a 2D vector by that matrix, that translated matrix up here. So can you multiply these two together? So that's going to be 1, 1. So that's a matrix notation for that. Can you multiply a 1 by 2 by a 4 by 4? You cannot do that. One of the numbers has to match the other number. So we have a 4 by 4 here, so we know one of these numbers has to be a 4. One of those has to be a 4, because both of these are 4. You can, using homogeneous coordinates, you can make a 2D vector. You can make that into 4D space. And in order to do that, you need to convert that to a 1 by 4 matrix. So that's going to be X, Y, 0, 1. The last one always normalizes to 1. And that's using the homogeneous coordinates. We just expand that to 4D space. So now that is 1 by 4. So now what we need to do is we need to multiply P times T, 1, comma 1. That's going to equal to, and I'm going to use white for the resulting one. Alright, so if you're familiar with, let's erase that actually. Let's expand this out just so you guys get a better idea. So we have 1, 1, 0, 1. Times 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 1, 1, 0, 1. Alright, now I'm going to do this as white. Actually green for the 1 by 4. So the inside numbers has to match. That's 4 by 4. So these 4 and 4, these have to match, and they do. So our resulting matrix is going to be 1 by 4. It's going to be these numbers here, 1 by 4. Alright, so what we need to do is we need to multiply the row of our position matrix, which is here, which we only have the row, so I'm going to switch this to blue. So multiply the row by the columns, and then add each component together. So multiply 1 by 1, and then add that by the multiplication of 1 by 0, add that to the multiplication of 0 and 0, and multiply that by the, or add that to the multiplication of 1 and 1. So let me bring up here white. Okay. So this is going to equal to 1. So 1 times 1, 1 times 1 is 1, plus 1 times 0 is 0, 0 times 0 is 0, 1 times 1 is 1. So it's going to be 1 plus 1 because the other two values were 0. Actually, let's move that down. So that is going to equal to 1 plus 1. So that is the x component. Alright, so now we need to repeat for the same. We only have one row here. We only have one row here. So we repeat the same process, but on this one, we operate on the second column. So let's put that back at white. So 1 plus 1 is equal to x. Now, we need to do the same thing. 1 times 0 is 0. Okay? 1 times 1 is 1. So that's 1. 0 times 0 is 0. 1 times 1 is 1. So that's going to be 1 plus 1. That's going to be the y component. Do the same thing for the third column. 1 here times 0 is 0. 1 here times 0 is 0. 0 times 1 is 0. 1 times 0 is 0. So that's 0. So that is the z component if we're using a 3D vector, or it's just a component we're not really interested in. Now the same row, since we only have one row in the position matrix, times the last column of the translation matrix. So 1 times 0, that's 0. 1 times 0, that's 0. 0 times 0, that's 0. 1 times 1 is 1. Alright, that's going to equal to 2, 2, 0, 1. And that is our result. X and Y are 2, 2. So our resulting one, P by the transform, is equal to 2, 2. So even though our initial value was 1, 1, we transformed it by the transform matrix, and that just adds 1 to each component. Things get more complicated when you bring scaling and rotation into the mix, but if you're just translating, it's just moving your original vector to another point. Okay, so this is a very basic overview. I'm probably going to create a few more videos depending on how far I get. But the most important thing I want you to remember is you can expand a 2D vector. A vector can be represented in matrix notation is what we did here. You can expand that to a 4-dimensional space by using the homogeneous coordinates. And the last number is always normalized to 1. So that expanded is going to be x, y, 0, 1. Now that we have that in a 1x4 matrix, we can multiply that by 4x4 matrix, which will give us a 1x4 matrix as a result, which then we can then pull the x and y values out of. So let me write up this formula here. Let's do that. So x is equal to the x translated is equal to the x original, which is that one here, times matrix 1, 1, which is here, plus y original, which is this here, times matrix 2, 1, which is here. 0 times 0 is 0, so don't need to add that to the multiplication or addition, since that's going to be 0 anyway. We're doing 2D vectors, so that's always going to be 0. If you're doing 3D, the math will be a little bit different. And then the last one, which will be just plus, that's always going to be 1. This is always going to be 1. And that's going to be 4m41. So that is the math to get the x translated result. Y translated is equal to x original times m21, which is here, plus y original, which is here again, times 2, 2, which is here, plus, that's always going to be 0, so that will be 0. And the last one is 1 by 1 as well, so that's just going to be plus m42. So that is the math for the y translated component. Is x times, 1, 2. 1, 2. So x original times m12 plus y original times m22 plus m42. That is the math for the y translated value. So this is just mathematics based on the translation. This is actually what monogame does directly. It's these two math operations. It doesn't actually do matrix 1 times matrix 2. It just does those two operations directly. So if you're working on if you're using DirectX or you're using some framework or a code that doesn't have a translation or transform a vector to a matrix, you can just do those two operations that way. Or you can set it up to where a 2D vector here is represented in a 4-dimensional matrix, a 1 by 4, and then you can multiply matrix A by matrix B. But the order that you multiply the matrix is important. The insides, 4 here and 4 here, the insides need to match. So that's it for this video. I might release more. You will definitely get this one. Hopefully you understood everything. I think the most important part is looking at a 2D vector and getting it to work by manipulating it by 4x4 matrix. Since it's a 2D vector, you can't really do that. You have to expand it to a 4D vector. And that is entirely possible by using the homogeneous coordinates. You just expand that. 0 will be the third component, and 1 will always be the last component. It'll always be normalized to 1. Once you do that, you just do matrix math like you've done before, and then you can write down the formulas like I had at the top right here. Alright, so next video we'll go into the actual coding, and we'll just call a dot transform, and we'll just call create translation. This is just for you to understand what goes on when you do matrix.create translation by a vector. How does that work? And what goes on when you call vector2.transform? How does that work? So this is just the mathematics behind the scenes of what's going on. So I hope you enjoyed this video, and stay tuned for the next one.